Our first gas law is a link between pressure and volume, assuming that temperature is fixed. Sometimes known as Boyle's law. And what we find is the pressure is inversely proportional to the volume for a gas of fixed mass, so we've got the same amount of gas in all of these experiments, we fix the mass, and constant temperature. And basically in this experiment we achieve that by making the changes in volume slow, so that the temperature inside the gas that we're studying it will equalise with the temperature outside. It's called. It will just, if it heats up, for instance, it would soon cool down again quickly to its surrounding temperature. So it stays fixed at that surrounding temperature. Now this can be written in equation form, and you can write it as PV equals constant. I'm not going to put that in a box yet for a reason. But basically what we're saying is if inverse proportion means as one goes up, the other comes down by the same amount, the same proportion. What that means then, if you multiply the two of them together, you'll always get the same answer. So if one's doubled, the other halves. When you multiply them together, the double and the half cancels out. And the equation that's most useful, the form that's most often used, and therefore the one that appears in the formula sheet, is this idea that we don't actually tend to bother working out the constant. We don't give it a name. But what we do is we compare pressure and volume at one point with pressure and volume at another. So the 1 and the 2 here, the subscripts, simply mean at one point. It'll become a wee bit clearer hopefully in an example. But pressure, usually in pascals, because we're dealing with direct proportion here, if you get pressure in other units, sometimes we come across units like bar or atmospheres, as long as it's the same in both sides, that's fine. It would cancel out in this relationship with these quantities. And similarly, the standard unit of volume is a cubic metre. But once again, as long as you're using the same units on both sides for pressure and volume, then that will cancel out. So, what do we mean by an example? So if we take a balloon, then if we imagine the pressure in a balloon is 2 times 10 to the 5 pascals, when its volume is 30 cubic centimetres. Calculate its volume when the pressure is 3 times 10 to 5 pascals. So when we're analysing this question, what we've got is two pressures and the volume, but the first pressure and the volume go together. So you're told that when the pressure is 2 times 10 to the 5, the corresponding volume is 30 cubic centimetres. You could pick 1 or 2, but I'm just going to call that pressure 1. And what matters is you make sure if you're calling that pressure 1, then volume 1 has got to be 30 cubic centimetres. Then the other pressure we've got is 3 times 10 to the 5 pascals, and we've been asked what would be the new volume at this pressure. So our formula, P1V1 equals P2V2, and then just substitute in their numbers. Okay, do what arithmetic you can, so we'll do the 2 times 10 to the 5 multiplied by 30. Then swap sides over to get V2 over on the left hand side. Then divide both sides by 3 times 10 to the 5. And that gives us a final answer, just to run out of space there, of 20 centimetres squared. And like I said, I can use the centimetres squared on both sides here, the cubic centimetres, sorry, because as long as I'm consistent on both sides with pressure and volume. We'll see that's not the case with temperature. We'll explain why that is when we get to that bit.